Hello, this is Dr. Eddie Morgan at Clovis East High School. Here to help you with your homework tonight. Tonight we're looking at the review for Unit 2, the first part of the review. And in this time, because I want you to do well on the test, we're actually going to go over exactly the problems that are on the homework. So let's get started. The first problem asks us to identify from each table of ordered pairs which ones are linear or nonlinear. So to be linear means that the rate of change is constant. In other words, as y changes and x changes, that's some number that's the same, okay? So let's take a look at the first one. For example, notice that this goes up by 1, plus 1, plus 1. And then over here, from 1.5 to 3, it goes up 1.5. 3 to 4.5 goes up 1.5. And up here 1.5. So notice that the change in y divided by the change in x in the first level is 1.5 over 1, and then it's 1.5 over 1 again, and 1.5 over 1. They're all the same, so we will say this is a linear function. Now you notice the next one, again, here we're simply going up by 1. Makes it easy to see what's happening here then. And here, notice to go from minus 9 to minus 2 is to add 7. And then from here to here, though, you're going to add 7 plus 2, so you went up 9. And then here from 7 to 15, you went up 8. So in this case, the change in y over the change in x is 7 over 1, and 9 over 1, and 8 over 1, and those do not equal each other. So this is non-linear. On the last one, once again, see the x's go up by plus 1, plus 1, plus 1. Our y's from 3 to minus 1 is going down 4, and then from minus 1 to 5 goes up 6, and then 5 to minus 9 goes down negative 14. So if I compare my rate of change, notice that it's changing. First, it's minus 4 over 1, and that does not equal 6 over 1, and that certainly doesn't equal minus 14 over 1. So this one, again, is non-linear. Okay? To be linear, the rate of change, how much y changes when x changes, has to be the same for all the points. Number 2 asks us to list the graphical characteristics of a linear function. Well, I would say the graphical characteristics is the graph of a linear function is a straight line. That's the easiest way to say it. One straight line. That is either increasing or decreasing, but not both. So it might look like this, or it could look like this, but it's a straight line going up or going down. We can't say this is linear if it goes this way. It can't be going straight up and down like this. That's no, because that's not a function. Problem 3 asks us to write the equation that represents the relationship below. Two things we need to know. We need to know what's the rate of change, and what is the y value when x equals 0. Once we know that, we can plug it into our equation, which says y equals mx plus b, and the rate of change is m, and this y value is b. Okay? So the rate of change is what we were doing just before. Notice that it goes up 1, 1, 1. At the same time, y is going from -3 to -2. It's going up +2, +2, +2. Notice they're the same. And my rate of change here, delta y over delta x, is 2 over 1. So my rate of change m is 2. Now to find that when x is 0, we just look up here. When x is 0, y is, b here is -3. Now we just plug those into here, and our equation is y equals 2x minus 3. And that's our equation for this relationship. 3b is like 3a, except instead of giving us a table, they've given us a graph. Now I could go through here and list all these in a table. That would be one way to do it. But another way to do it is, once again, we need to find the rate of change. And in a graph, that's called the slope. And we're simply asking, how much does it change between points? So in other words, if I look here, if I go over 1, y, it goes up. Notice I go over 1 here, it goes up 2. So my change in y over my change in x is 2 over 1, just like the last one. Now, what's the y value when x equals 0? Well, what we can do is draw our line here, and we notice that if I use the slope and go backwards, if I go down 2 and over 1, when x is 0, y is 0. It goes to the origin. So that's going to be 0. So now we substitute that into our equation, and we have y equals 2x plus 0. The 0 is extra here, and we can just write y equals 2x. And that's our answer. Problem 4 gives us some sets of ordered pairs and asks us to describe which ones are functions. Remember that for ordered pairs to be a function, every x has to have only one y. We can have multiple y's, but we can't have an x with two y's. Let's do this by setting up just a mapping here. So if I go to number A first, and I set my x's and y's up here, I have 1, 0. I have 1 again, so I don't write it again, 1, 1. Then I have 1, 2, and I have 1, 3. Now notice that 1 maps to 0, 1 maps to 1, 1 maps to 2, and 1 maps to 3. That can't happen. All right? You can't have an x have two values. So this one is no, so this is not a function. When we go to B, our x values are 0, 1, 2, 3, and 4. Our y values are 1, 2, 3, 4, 5. And notice 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 to 4, and 4 to 5. Every x has just one value of y. So this is a yes. So this one is a function. For C, we have x and y. We have -1. Well, actually, I'm going to put them in order. So I have -3. That's the smallest one. Then -1. Then 1, 4, and 5. And then my values here, I have 0, 0, 0, and 3. Okay? So you might be thinking, oh, that looks like A. But you got to realize I can have multiple y's. I can't have multiple x's. So 3, my -1 goes to 0. So that goes there. 1 goes to 0. 4 goes to 0. And 5 goes to 0. And -3 goes to 3. Now, even though several of them go to 0, you'll notice that no x has more than one value of y. So that makes that a function. And finally, D, I have 1, 2, 3 for X. 1, 2, and 3. And my values here are 2, 3, and 5. So first of all, 1 goes to 3, and then 1 goes to 2. 2 goes to 2, 3 goes to 5, and 3 goes to 5 a second time. That's okay because it's the same thing, but here's our problem right here. 1 to 2 and 2 to 3. You can't have one value going to two values. So this is no, this is not a function. Problem 5 says, how can we determine if a relation is a function? Algebraically and geographically. Well, algebraically, we take a look at our x and our y's, okay? So if we have a bunch of numbers here, 1, 2, 3, 4, if every y, let me just put in any numbers here, if every x just goes to one y, okay, even if this one goes to 2 here, this one goes to a y there, if every x goes to one y, then that's a function. However, if we did that again, and suppose we had 1 went to 2 and 1 went to 8, now notice this x goes to two y's, and so that is not a function. So that's how we do it algebraically. Graphically, we use the vertical line test. Which means if I have a graph like this and it goes like this, notice that if I draw vertical lines, anywhere I cross, it only crosses one time. So that is a function, all right? On the other hand, if I have a graph that looks like this, I may draw where it goes through once, that's fine, and once, fine. But notice right here, it went through more than one time. And so that would not be a function. That would be no. Problem 6 asks us to graph the function first and then determine if it's linear or nonlinear. Well, that's easy. Okay, this is our x value and this is our y. We always graph x first. So 1 over 1, and then down 7. 1, 2, 3, 4, 5, 6, 7. So there's our first point. Second point is 2 minus 6. So 1, 2 over 2. 1, 2, 3, 4, 5, 6. Second point. Third point is 3 minus 1. 1, 2, 3 minus 1. And we can already begin to see we're in troubles if we think that's going to be a straight line. So the last one is 1, 2, 3, 4, and 1. Now just noticing here, at this point, if I were to draw a line through these 2 points, notice it doesn't catch those. So if I'm asking, is the function linear? No, it is not linear. If I want to check it algebraically, I can always go up here and check my change in y over my change in x. Notice that goes 1, 1, 1, but here it goes up plus 1, but here it goes up plus 5, and then here it goes up plus 2. So you can see that my minus y, my change in y over my change in x, the first one it's 1 over 1, but then it goes up 5 over 1, and then it goes up 2 over 1. So even from algebraically, I can see this is not going to be linear. The rate of change is not the same. It's not constant. Problem 7 asks us to first make a table of 3 values for the function rule and then graph the function. So we're going to start here. We've got an interesting situation here. We have negative 3/5 x. Well, if I'm dealing with that and I'm going to multiply by x, and if I don't want to get my answer to be fractions, what could I use? Well, the answer is right there. Use multiples of 5, because then we'll get whole numbers. So I'm going to choose minus 5, 0, and 5. So let's try the first one. Minus 3/5 times negative 5 plus 1. Notice that 5 goes into negative 5 minus 1 time, So negative 3 times negative 1 is positive 3, plus 1 means that that's going to be the number 4. Now we put in 0. Minus 3/5 times 0 plus 1. Well, anything times 0 is 0 plus 1. It's going to give me 1. And then for 5 divided by 5 is 1, so I get minus 3 plus 1. Minus 3 plus 1 is minus 2. So there are my 3 points. So let's graph them. Minus 5, 4. So starting with 0, going x along the variable here and y up. 1, 2, 3, 4, 5. And then we're going to go up 4. 1, 2, 3, 4. That's our first point. Next one is 0, 1. And then 5 minus 2. 1, 2, 3, 4, 5. And then down 2. And if you notice here, if I were to draw my line here, I got a straight line going through there. This is a linear function. Number 8 asks us to determine whether a relationship is continuous or discrete. Discrete means it goes by step. For example, a discrete function might be if I'm measuring the number of cars I wash. I either wash 1, 2, 3. I don't wash 1.5. Whereas if I want to measure how long does it take me to run, my time doesn't change even by seconds. It can be even milliseconds. So let's start. The height of the German Shepherd General Sherman tree over the last 100 years. Well, a tree, sorry about the funny tree, but as a tree grows, it grows continually. It doesn't every one day just jump 2 inches. So this is continuous. On the other hand, the number of cookies Stan bakes, that's going to be discrete. As Stan puts them on the cookie pan, he's going to put 1, 2, 3, 4, a dozen cookies or so, but he's not going to put half cookies on there. Same with the number of cows. He counts how many cows he has, and he gets a whole number, an integer, 1, 2, 3, 20, 30, 50, but he doesn't have 20.5 cows. However, the distance a runner runs, he could run 1 mile and then run 1 mile and a little bit more, and so the distance is continuous. Number 9, Alyssa earns $5 per hour babysitting. Write a rule where P is her total pay and H is her number of hours. So how are they related? All right. So she makes $5 per hour. And she works so many hours, and we want to know what her total pay is. If you look at the units here, dollars per hour, an hour, notice that if I multiply them together, the hours will cancel out. In other words, $5 times her hours will equal how much pay she gets. If you're not sure about it, think about it in terms of, if she works 1 hour, she makes $5. If she works 2 hours, she makes $10. If she works $3, she makes $15. If she works 8 hours, she makes her pay. In other words, our formula, if we write it the other way, is her pay is going to be 5 times her hours. Problem 10 says that a lawn care company charges a $10 trip fee plus 15 cents per square foot of X square feet of lawn. Write an equation. Well, the first thing to notice, if my cost here, and I'm going to let cost, the cost for this thing is going to be, first of all, it's going to be the trip fee, plus it's going to be the 15 cents times however many feet I use. So if I'm going to let trip fee, we said the trip fee was $10, and I'm going to let C be the cost, I end up with cost equals 10 plus 0.15x. And often as mathematicians, we like to put the x first. So I'll write it as 15x plus the 10. And that's our equation. Problem 11 is similar to problem 10. We have the total cost that a painter charges you to paint his house. It depends first of all upon H, the number of hours it takes to paint the house. And your house, the painter charges $2.50 for supplies and $15 per hour. So the $2.50 is a fixed amount. He's going to charge you $2.50 no matter what, and then he's going to charge you $15 per hour. So notice that the cost is going to be the $250 plus $15 per hour. So that's going to be $15, and that's going to be times the number of hours. So to write this cost as we usually do, cost equals, I'm going to put the variable first, 15h plus 250. That's going to be my function. Now the second part says, what happens if he works 30 hours? Well, we just plugged the 30 into h. So C equals 15 times 30 plus 250. Well, 15 times 30 is going to be $450 plus the 250, and our answer is it's going to cost us $700 if he works 30 hours. Problem 7 says to find the range of the function for the given domain. The domain is here. That's our x values. It wants to find then our range is our y values. If you remember our video, the domain is the chickens in and the range is the chicken nuggets out. All we have to do is take each of these and plug them into here and find the value. So f of minus 2 is going to be minus 5 times minus 2 minus 7. Minus 5 times minus 2 and negative times a negative is positive. So that's going to be 10 minus 7 or 3. Now let's plug in 0. F of 0 equals minus 5 times 0 minus 7. Any number times 0 is 0 minus 7. Our answer is negative 7. And then f of 1, minus 5 times 1 minus 7. So that's negative 5 minus 7. It's going to be negative 12. And then finally 2. F of 2 is minus 5 times 2. Minus 5 times 2 is going to be negative 10 minus 7, negative 17. So our answer, our range, and I'll use the set notation here, is going to be, let's put them in order, minus 17, minus 12, minus 7, and 3. That's our range. Number 13 asks us to write the explicit and the recursive formulas for the arithmetic sequence. If it's an arithmetic sequence, it means it has a common difference between the two. So if I want to find this, there's only two things I need to know if I want to write the formula. Let me just write it out here so it's bigger to see. The two things I need to know is, first of all, what's the first term? A of 1 means the first term, and the first term is 13. The next thing I need to know is what's the common difference. We'll write that as D. And notice to go from 13 to minus 7 means I subtracted 20. 7 to minus 20, subtract 20. Minus 27 to minus 4 minus 20. So my common difference is negative 20. Okay? Now it wants the explicit first. So the explicit formula is the nth term. Remember, A of n, this is not A times n, this is A of n, it's the nth term, equals the first term plus n minus 1 times d. So what I need to do is simply plug in A1 and d. So my answer is a to the n power equals 13 plus n minus 1 times minus 20. Very important that you put the parentheses there. Otherwise, it'll look like n minus 1 subtract 20. We're multiplying by 20, so you got to put that down. So there is our explicit. Let's write it down here. A of n equals 13 plus n minus 1 times minus 20. Our recursive, for the recursive, we say that the nth term equals the n minus 1 term. That's the previous term. See, if I want to find the 50th term, the 50 minus 1 is the 49th term, the term just before it, plus d, and then I need to say where it started, so I'll have to put in my a1. Okay? So my recursive here is going to be a to the n equals a to the n minus 1 plus d. Okay? And in this case then, what's my d? So let me just erase that for a moment. I don't need that. I'm erasing that. I need to put in my d, and my d was minus 20. And my a1 then is a1 equals 13. Now I can rewrite this instead of plus minus 20. I can say a to the n equals a to the n minus 1 minus 20. And then a to the 1 equals 13. And that's my answer for the recursive. A to the n equals a to the n minus 1, subtract 20, and a to the 1 equals 13. Now for 13b, we'll repeat the process we did for 13a. All right, so I'm going to write this out so it's a little bigger to see. Minus 2, 1, 4, 7. And the things we need to know is, first of all, we need to know what's the first term. And we look here and we see that our first term is minus 2. The second thing we need to do is find out what's the common difference. Because it's an arithmetic sequence, there's a common difference. So if I look here, to go from negative 2 to 1, I add 3. From 1 to 4, I add 3. And from 4 to 7, I add 3. So D is 3. Okay? Now, our explicit formula has the form the nth term equals the first term, a of 1 means the first term, plus n minus 1 times d. So all I have to do is plug in my a1 and my d. So my answer is a to the n, the nth power, is the first term, and the first term, remember, is minus 2, plus n minus 1 times d, and my difference here is 3. I'll put it in parentheses to remind me that I'm writing that I'm multiplying. So my answer here for the explicit, a to the nth power, equals minus 2 plus n minus 1 times 3. For my next one, for my recursive, the model form for that is that the nth term equals the previous term, n minus 1 term, plus the d, and then we need to state that the a, whatever a1 is. So in this case, I need to put an answer for there and for there. Substitute again from what I know. So my answer is the nth term equals a to the n minus 1 plus, and in this case, my d is 3. And then I state that my a1 equals minus 2. And so there's my recursive formula. an equals a to the n minus 1 plus 3, and I state that a1 equals minus 2. Problem 14 says to write the recursive formula for the arithmetic sequence, and it gives us the explicit. Well, you remember the explicit is written like this. A to the n equals a to the 1 plus n minus 1 times negative 2. So notice something here. This tells me that my a1 term equals 5 and my d equals minus 2. So now I can write the recursive because I know those two pieces of information. And the recursive says that the nth term equals the n minus 1 term plus d, and then we state the a1. So simply substituting in here, a to the n is going to equal a to the n minus 1 plus d, which is going to be minus 2. And then I'm going to state that my a1 equals 5. And that's going to be my answer. Problem 15 is a word problem. It says every time a touchdown is scored in a football game, 6 points are added to the score. A team already has 12 points. Write an explicit formula that represents the total number of points. Remember, our explicit says that the nth term equals the first term plus n minus 1 times the common difference. So what's our first term here? Well, our first term says that they've already scored 12 points. So that's going to be 12. And then our common difference is it goes up 6 points each time. So those are the two things we're going to plug into there and to there. And so our answer is a to the n equals a1, which they already started with 12 points, plus n minus 1 times the number that it keeps going up by is 6. And so there's our explicit formula for the problem 16. Asks us to draw the next figure in the box. Notice here's diagram 1. And then when I go to diagram 2, what changed is I added one on that end and I added one on that end. When I went here, again, I just added another one. So my next diagram, instead of having 4 along the bottom, is going to have 5. So 1, 2, 3, 4, 5. And likewise up here, 1, 2, 3, 4, 5. Okay? So that's my next diagram. When I want to complete the table, notice diagram 1 has 3 boxes. Diagram 2 has 5 boxes. Diagram 3 has 7 boxes. And diagram 4 had 9 boxes. If I write this as a sequence, it went 3, 5, 7, 9. And I should begin to notice, oh, each time I'm adding 2. So my next 7 figures are going to be 11. 11 plus 2 is 13. 13 plus 2 is 15. Now, if I want to write a recursive, I need to know, first of all, where did it start? Well, the first term, remember, was 3. So that's going to be 3. And then, what's the common difference? Well, the common difference is it's going up by 2. So my common difference is 2. So now I can write my recursive. My recursive is a to the n equals the previous term, n minus 1 term, plus d. And then I state what a1 is. So in this case, my answer will be a to the n equals a to the n minus 1 plus, it goes up by 2. And then my a1, where did it start? It started at 3. And that's our answer. All right. I hope this helps you. Just a reminder, these review problems were actually kind of taken from the test that you're going to take next. So if you know these review problems, you're going to do great on the test.